So now moving from actual titration questions to a little bit more sophisticated type calculations, although titration data might feature in these a bit. So something already done, write an expression for the ionic product of water given the units. Well, here's water dissociating to H3O plus OH minus. So Kw is the H3O plus times the OH minus, or you might remember you could just use the H plus times OH minus. Don't include the water on the bottom because it's a pure liquid, so we leave it out by convention. So the units, we got concentration and concentration, so it'll be moles per cubic decimeter squared, or mole squared cubic decimeter to the minus 6. Value for Kw at 298, 1 times 10 to minus 14. So why does the pH of pure water at this temperature have a value of 7? Well, in pure water, the H3O plus and the OH minus concentration are equal. Kw, 1 times 10 to the minus 14, equals the H3O plus concentration times the OH minus concentration, but the OH minus concentration is equal to the H3O plus concentration. So 1 times 10 to the minus 14 is the H3O plus concentration squared, or in other words, the H3O plus concentration is the square root of 1 times 10 to the minus 14, which is 1 times 10 to the minus 7. pH is, of course, minus the log of the H3O plus, so minus the log of that, which is 7. Change the temperature, change Kw, change the pH of neutral solutions or pure water. Calculate the pH of the final solution if 10 cubic centimeters, 0.1 molar HCl added to 990 cubic centimeters of pure water. This is actually a rather bad question. The dilution equation is fine. New concentration times the new volume is the old concentration times the old volume. Divide both sides by the new volume and you get this. Old concentration 0.1, old volume 10 cubic centimeters. New concentration, they're assuming that you can just add the volumes. Volumes are not necessarily additive, so to expect you to do this is rather naughty, but we'll do it. 990 plus 10 is of course 1000, and so we find our new concentration 0.001 moles per cubic decimeter. pH, therefore, is minus log of that, which is 3. And calculate the pH of solution, which is 0.01 moles with respect to ethanoic acid. That's the Ka of ethanoic acid, and 0.2 moles per cubic decimeter of sodium ethanoate. Well, here we use the Henderson-Hasselbalch equation. pH is pKa for the acid plus log of the base concentration over the acid concentration. Throw in everything we know and we get 5.05. I really don't like using the Henderson-Hasselbalch equation, but in this case it's adequate because we can look at this Ka value and know that it's pretty small. If Ka is not very small, well then this becomes a much nastier type of question that the A-level use of the Henderson-Hasselbalch equation does not address. And finally, 10 moles 0.1 is added to 990 cubic centimeters of this solution. Describe then the change in pH is only 0.06 instead of 3 going to 5.5. Explains why this change in pH is much smaller than in B2 than this one here. Okay, and the reason being is because it's a buffer solution. You've got lots of the ethanoic acid, 0.01, and conjugate base ethanoate 0.02. So it's a 2-to-1 buffer solution. Because of that, when we add the HCl is going to be neutralized by the ethanoate, okay, by the base. So the reaction changes a little bit, but all of this big HCl that's added has gone. So all that happens is that you've turned the strong acid into the weak acid. So the weak acid only generates a little bit more H3O+. Sulfur dioxide, react with oxygen and water, form sulfuric acid. Although sulfuric acid is a strong acid, it doesn't have to be concentrated. So we've actually answered this question previously, just from the other perspective. A strong acid completely dissociates, so the concentration of H3O plus is the initial concentration of the acid. A concentrated acid is one that has a high initial concentration of the acid. It implies nothing about the H3O plus. Strong acid is talking about the acid. Concentrated is just talking about the particular solution you're looking at. Let's Student given aqueous solution of monoprotic acid, asked to find out strong or weak. 25 cubic centimeters of the acid required, 15.9 cubic centimeters of sodium hydroxide for complete neutralization. Calculate the concentration of the acid. Well, we know it's monoprotic, HX, so it needs 1 NaOH to neutralize it. So moles of NaOH are the volume, 0.0159 cubic decimeters, times the concentration, 0.0125 moles per cubic decimeter. So that's 1.99 times 10 to the minus 4 moles of NaOH. And that is, of course, equal to the moles of the acid. So the moles of the acid is the concentration of the acid, 1.99 times 10 to the minus 4, divided by the 25 cubic centimeters, 0.025 cubic decimeters, which is 0.00795 moles per cubic decimeter. Remember that number. There's the number there in case you forgot it. Teacher measured the pH of the solution and found it to be 2.1. She told the student the acid in the solution must be strong. Is she correct? And justify your answer. Well, if it's a strong acid, that means that all of the original acid dissociated. So therefore, 0.00795 moles per cubic decimeter would have been the concentration of the H3O+. pH is minus the log of that, which is 2.1. So therefore the teacher is correct. Okay, we determined the initial concentration of the acid, 0.00795. All of that, if it's strong, becomes H3O+, so the H3O+ concentration is 0.00795, which is a pH of 2.1. Okay, thus pH measured is the pH expected from a strong acid. So the teacher, shockingly, is correct. Fluorine can form hydrofluoric acid HF, Ka value of 7.2 times 10 to the minus 4 moles per cubic decimeter. Write an expression for the Ka. Well, we got HF reacts with water. We're told it's a weak acid, so it's a reversible. We're told it's an acid, so that means H3O+, because the HF has donated a proton to the water, leaving behind F-, the conjugate base. Calculate the pH of a solution of this. Well, concentration of the HF is 0.1, none of the H3O+, none of the F-, minus X, X, and X, 0.1 minus X, X, and X. Throw that into our little equation, and we get 7.2 times 10 to the minus 4 is X times X over 0.1 minus X. Now, if you are doing this the A-level way, you wouldn't even worried about the X there. You would have just said that X is going to be the square root of 0.1 times 7.2 times 10 to the minus 4. And to get to that 0.1, you would have had to ignore this minus x. And to ignore this minus x, you would have said this is small enough that at equilibrium there's not very many products, so x is small, so 0.1 minus x is about 0.1. Doing that, you get x is 8.48 times 10 to the minus 3. So what you've said is that x 8.48 times 10 to the minus 3 is so small that when we take it away from 0.1, we get 0.1. Well, trouble is though, after we take that through, pH is 2.07, and then we check our assumption, what we find is that the error is actually 8.4%. That's too big. You can't make this assumption that taking 0.00848 away from 0.1 is a reasonable measure. So what we have to do is if we're going to do this properly, and I should emphasize this would be the A-level answer, but I should emphasize that if you are a true chemist, you would look at this error, 8.48%, and say, let me do this properly. And properly requires that you solve the quadratic equation. You don't forget this minus x. You multiply this all out, you get this gross looking equation here that you throw in. So we've got b is 7.2 times 10 to the minus 4, minus that. B squared, 4 times a, which is 1, times c, which is minus 7.2 times 10 to the minus 5. Solve that, and we get x is 8.13 times 10 to the minus 3 molar, and so the pH is 2.09. 0.02 difference in the pH, you might say who cares, but a significant difference, 8.13 versus 8.48 in terms of the value of X. Okay, A-level, you wouldn't have needed to do this. Proper chemistry, you should have done. Concentration of hydrofluoric acid found by titrate against sodium hydroxide. Not all acid-base indicators would be suitable. What features would make an indicator suitable? Well, a weak acid titrated with a strong base. At the equivalence point, all you've got is the conjugate base because all the weak acid has been neutralized. So its equivalence point greater than 7. Okay, you want the indicator to change color around the equivalence point. Now, HF is a pretty good weak acid, which means its conjugate base fluoride will be a pretty bad weak base. So therefore, the equivalence point will be between about 7 and 10. So it's got to be greater than 7, but it won't be hugely greater than 10 because it's a very, very weak base. So you want the color change of the indicator to be between 7 and 10. Here we are talking about buffer solution again. You're going to have HF plus water, H3O plus F minus. As we start titrating the hydrofluoric acid, the HF, every bit of the HF that gets neutralized by the hydroxide gets turned into F minus. So you very quickly get a buffer solution that has got HF and F minus. Again, if we add a strong acid, we've got enough F minus there to neutralize it, so the reaction goes initially to the left, right? If we add a strong base, we've got enough HF there to neutralize it, so the reaction initially goes to the right, making F minus, in this previous case making HF. Then of course the equilibrium reestablishes itself, but not generating huge amounts of H3O plus or OH minus. Thus the result of the effect added acid or base significantly reduced. So finally, a fun little question. We're taking sodium hydroxide, adding it to HF. We know that every bit of the sodium hydroxide that we add neutralizes hydrofluoric acid, turning it into its conjugate base, fluoride. Okay, calculate the pH of the buffer solution. Well, here's the equation of interest in the buffer solution. We need HF and we need F minus. The new HF concentration was, we took 25 cubic centimeters of 0.1 molar, but now it's diluted to 12.5 plus 25 cubic centimeters. Its new concentration is 0.0666. The sodium hydroxide that we added, and remember every bit of the sodium hydroxide added neutralizes HF, turning it into fluoride. So that's 12.5 cubic centimeters times 0.1 moles per cubic decimeter, and we got 12.5 plus 25 again is the new volume, and that's 0.0333. So what we find here then is that this is half the equivalence point. We've added half as much OH minus that we needed to react with all the HF. At the half equivalence point, pH equals pKa, so pH is minus the log of 7.2 times 10 to the minus 4, which is 3.14. Hopefully that was fun. Awful lot of stuff in this acid-base review, but when you think about it, it actually just focuses on 4 or 5 essential points.